In this lesson, we're going to explore the exponential function and we're going to look at how we can differentiate exponential functions. So we're going to start with this interesting function here where we've defined f of x to be 1 plus, and then we've got ascending powers of x and increasing factorials. Now we could in fact eliminate this 1 and replace it with x to the power of 0 over 0 factorial, and that fits the sequence quite nicely. This is x to the power of 1 over 1 factorial. Now because this is a sum where the terms are quite similar, we've got a variable here that seems to increase every time, which we'll call n. We use this sigma notation. Let's let n go from 1 to wherever we want to go to. On the calculator you can see here we've gone from 1 to 10, so that's the first 10 terms. X to the power of n over n factorial. Now you can see on the calculator here we've got this plus 1, but we could use this version and not have the plus 1. So if we say we're actually going to go from n is 0, then we don't need that plus 1 because x to the power of 0 over 0 factorial is 1. Whichever way you do it, try it on your calculator and you'll see that you get this value here, 2.718. Now if you also put in your calculator e to the power of 1, or just e, this is 2.718. What we're showing here is that this interesting function with these powers of x and factorials is one way of calculating e to the power of x, or in this case e to the power of 1 is also approximately 2.718. We'll try this for a couple of different values. In this one we've assigned 3 to x, so x has a value of 3, and we compare that with e to the power of 3. So when we say 1 plus 3 over 1 factorial plus 3 squared over 2 factorial, it's approximately equal to e to the power of 3. And again, you could use my version of the formula, replace the n equals 1 with n equals 0, and then you don't need the plus 1, you should still get the same value. So what we're showing here is that f of x is equal to e to the power of x, or that f of x tends to e to the x as n tends to infinity. Indeed, if you increase this value 10 to a much higher number, you should see that it is much closer to e to the power of x. Why don't you try some higher values instead of 10 and watch that approximation tend to e to the power of x. Just to confirm this result, we'll also try some negative and non-integer values for x to make sure that this function does still work. So we're trying to show, remember, that f of x is approximately equal to e to the power of x for different values of x. So just try a few different values on your calculator. Here we've tried -1 and 0.5, but you should also try some different numbers to satisfy for yourself that f of x does indeed approximate e to the power of x. Now we're going to consider differentiating this function f of x. So we'll look at each term one by one. The derivative of 1 is 0, and remember, when we're differentiating we reduce the power of x by 1 and multiply by the original power, so x to the power of 1, but if we multiply by 1 and reduce that power by 1, we've now got 1 times 1 over 1, which is 1, multiply by the power, reduce the power by 1, so x squared differentiates to 2x over 2 factorial, then we've got 3x squared over 3 factorial, 4x cubed over 4 factorial, and so on. Now if we simplify this series, obviously the 0 we don't need to write down, 1 is fine, 2x over 2 factorial the 2's cancel, and this is just x. Now if we look at 3x squared over 3 factorial, remember 3 factorial is 3 times 2 times 1. So if we cancel the 3's, this is now x squared over 2 factorial. And similarly, if we cancel the 4's, 4 factorial is 4 times 3 times 2 times 1. So if we cancel the 4, that's 3 times 2 times 1, or 3 factorial. So now this is x cubed over 3 factorial. 5x to the 4 over 5 factorial simplifies to x to the power of 4 over 4 factorial. Now look at this series and compare it with f of x. It's the same thing. So we took f of x, we differentiated each term and simplified, and the result was f of x. And remember, f of x was e to the power of x, and when we differentiated f of x, it was e to the power of x. So what we now have is, when we differentiate with respect to x, e to the power of x, we get e to the power of x. And this is a result which is another definition of e to the power of x. It's a function which differentiates to itself. So now let's look at some examples. We're going to differentiate each of these with respect to x. So number 1, we're differentiating with respect to x each time, and we've just got 2 terms added together. X cubed differentiates to 3x squared, and e to the x differentiates to e to the x. And the second one, we've got 5e to the x. When we differentiate this with respect to x, we get 5e to the power of x. In the third example, we've actually got a function in our index. So I'm going to say that this is the derivative with respect to x of e to the power of u, and we'll define u, we'll say let u is x squared take 5x plus 1. Now we can use the chain rule. So if y is e to the x squared take 5x plus 1, dy by dx, using the chain rule, is dy by du multiplied by du by dx. So dy by du, y is e to the power of u. So dy by du is e to the power of u. Remember, when we differentiate e to the power of x, we get e to the power of x. So when we differentiate e to the power of u, we get e to the power of u. And then we multiply this by du by dx. And remember, u is x squared take 5x plus 1. So this is 2x take 5. And remember to use brackets here. It's not e to the u times 2x and then subtract 5. It's e to the power of u multiplied by this whole expression. So now we need to substitute back in our u, and I'm just going to rearrange it slightly. So we've got 2x take 5 multiplied by e to the power of x squared take 5x plus 1. Now if you compare this with the original expression that we were differentiating, we've got e to the power of x squared take 5x plus 1, and when we differentiate it, we've left the e to the power of x squared take 5x plus 1, and we've multiplied by the derivative of that expression in the index. And this is a general. So in general, if we have a function which is in the form y equals e to the power of some function of x, then the derivative of y with respect to x is the derivative of that function of x multiplied by the original e to the power of f of x. And we can now use this rule in subsequent similar examples. So try them on your own first, and then have a look at my solutions. So here we've got e to the power of 5x take 2. When we differentiate that with respect to x, because f of x is 5x take 2, f dash of x is 5, and then it's e to the power of the original function. In number 5, when we differentiate with respect to x, this time our f of x is x squared plus x, so f dash of x is 2x plus 1, and our original function e to the power of x squared plus x. Remember, in this case we do need brackets. It's the derivative of f of x, the whole thing, multiplied by e to the original f of x. And then finally, if you look at number 6, we actually have a product here. X squared e to the x is a product of two functions of x. So if you remember the product rule, when you've got y as two functions of x multiplied together, dy by dx is the derivative of the first function multiplied by the second function plus the derivative of the second function multiplied by the first function. So applied to this example, the derivative of x squared is 2x multiplied by e to the x plus the derivative of e to the x is e to the x multiplied by x squared. And we'll just tidy this up by factorising at the end. E to the x and x are factors of both terms, so x e to the power of x multiplied by 2 plus x. We'll conclude this lesson with an application of the derivative of the exponential function. From the sketch, there appears to be a turning point, but we're asked in the question to prove that there is only one turning point and to give the location of that turning point. We need to find where the gradient of the function is 0. That means differentiating. So if we take our y equals e to the x over x, notice that it's a quotient, so I'm going to use the quotient rule. Remember, for the quotient rule, if you've got y is u over v, where u and v are functions of x, then dy by dx is u dash v take v dash u all over v squared. So our dy by dx, derivative of e to the x is e to the x, multiply by the denominator, subtract, the derivative of the denominator is 1, multiplied by e to the x, all over the denominator squared. Now I need to look at values of x when this equals 0. So this is why factorising the expressions is useful, because that means we can use the null factor law. So if I factorise the numerator, e to the x multiplied by x take 1, all over x squared. Now for this to equal 0, we need either e to the power of x to equal 0 or x take 1 to equal 0. Now if you remember, e to the power of x, it's an exponential function. If we graph it, it looks roughly like this. And e to the power of x actually can never equal 0, because we have a horizontal asymptote here. So e to the x can't equal 0. That means that x take 1 must equal 0, and therefore x equals 1. And that's the only solution for this derivative equaling 0. Clearly the denominator can't equal 0, that wouldn't be possible. E to the x can't equal 0, so x take 1 must equal 0. So now we have the x value of our turning point. We substitute back into the original equation, so e to the 1 over 1, which is just e, and therefore our turning point is 1e. There's no need to express e as a decimal, because any decimal value would be rounded and therefore not accurate. E is an exact value, so this is absolutely fine as the solution to this problem.